Hello, hi everyone. Welcome to this online video classes. This is Dr. U. Raghavendra, Assistant Professor of Chemistry, MVS Government Degree and PG College, Mahabub Nagar, Telangana. In this video, I would like to explain about part 6 of coordination compounds. Till now, I developed 5 videos on coordination compounds. In part 1 of coordination compounds video, I explained about introduction and importance of coordination compounds as well as the terminology which is used in coordination compounds or coordination chemistry. In part 2 of coordination compounds video, I explained about the nomenclature and also about the Werner and Sedgwick theory and also about effective atomic number. In part 3 of coordination compounds video, I explained about valence bond theory and its applications to 4 coordinate as well as 6 coordinate complexes. In part 4 of coordination compounds video, I explained about the isomerism in coordination compounds. In part 5 of coordination compounds, I explained about crystal field theory and its applications to 4 coordinate as well as 6 coordinate complexes. Okay, next. In this video, I would like to explain about magnetic properties of transition metal complexes. And also I would like to explain about spin only formula and calculation of magnetic moments of some transition metal complexes and also about determination of magnetic susceptibility, that is the Gouy method. Okay, fine. Next, here, based on the interaction of the substances, generally based on the interaction of the substances or compounds with the external magnetic field, the substances classified into various types. Here generally the magnetic property of substance generally depends on the arrangement of electrons in given compound or in a given substance. Okay, fine. Here, based on the arrangement of electrons, the substances are classified into different types. If you observe them, the first one is diamagnetic substances. Here, the substances which have all paired electrons, generally known as diamagnetic substances. If we place these substances in external magnetic field, they are repelled by the external magnetic field. Okay, that is in the case of diamagnetic substances. If we place them in the external magnetic field, they are repelled by the external magnetic field because these compounds have completely paired electrons. So they are repelled by the external magnetic field. If we place the external magnetic field, if we place the diamagnetic substance in an external magnetic field, then there is an induced magnetic field developed in the compound. Here, the induced magnetic field strength of this substance generally less than that of the external magnetic field strength. That is, in the case of diamagnetic substances, if you place the substance in the external magnetic field, the magnetic field induced in the substance always contains less strength than the external magnetic field strength. That is, if you take difference delta H is equal to B minus H0, here B is the induced magnetic field strength which is produced in the substance in the presence of external magnetic field. H0 or H0 is the strength of the external magnetic field. If you take difference, then delta H is equal to B minus H0. It is always negative. In the case of in diamagnetic compounds or diamagnetic substances, the difference in between the induced and external magnetic field strength is always negative. Here the diamagnetic substances or diamagnetism does not change with change in temperature. If you change the temperature of the diamagnetic substances, then there is no change observed in the diamagnetic property of that particular substance. Okay, if you observe the examples for diamagnetic substances, they may be lithium plus copper plus magnesium plus 2 ions, or they may be, if you observe some complex, it may be hexacyanoferrate, hexaamine cobalt ion, or we can take some rubber, wood, as well as N2 gas. All these are the example for diamagnetic substances. Generally the magnetism or the magnetic property of any substance is, it is due to the arrangement of electrons in that particular substance. Generally the magnetism or magnetic property of any substance is well known only if we place the substance within the external magnetic field only. Otherwise we don't know the magnetism, whether it is para or dia, without taking the substance into the external magnetic field. Okay, it is essential to place the substance in the external magnetic field in order to know the magnetism of that particular substance. Okay, fine. Next, paramagnetic substances or paramagnetism. These substances generally have few or more than few unpaired electrons. Generally paramagnetic substances have unpaired electrons, so these are attracted by the external magnetic field. If you place paramagnetic substances in external magnetic field, they are attracted by the external magnetic field. It is due to the alignment of the induced magnetic field with external magnetic field vector, so they are attracted each other. In the case of diamagnetic substance, the arrangement of the induced magnetic field direction and external magnetic field direction are quietly antiparallel, or they are opposite to each other, so they repel each other. If the induced and as well as the external magnetic field vectors are in same direction or they are in parallel direction, then they attract each other. When they are antiparallel, they repel each other. In the case of diamagnetic, it is antiparallel, so they repel each other. In the case of paramagnetic, induced as well as external magnetic field or in a aligned direction or in parallel direction, so they are attracted each other. Okay, if you place the paramagnetic substance in an external magnetic field, then the magnetic field induced or produced within the substance, if you take it B, generally it is more than the external magnetic field strength. That is, the induced magnetic field strength of the paramagnetic substance generally always greater than that of the external magnetic field. That is, B always greater than H naught. But in the case of diamagnetic, B always less than H0. So in the case of diamagnetic substance, the difference in between the two field strengths is always negative. But in the case of paramagnetic substances, if you take difference, that is delta H, is always positive. That is, the difference in between the induced magnetic field strength and external magnetic field strength is always positive in the case of paramagnetic substances. Here the paramagnetism inversely proportional to the temperature. In the case of diamagnetic substances, it does not depend on the temperature, but paramagnetism depends on the temperature and inversely proportional to the temperature. That is, if you raise the temperature, it will be decreased. if you decrease the temperature, the paramagnetism will be increased. That is, it is inversely proportional to temperature. So it increased, it decreased. That is, paramagnetism decreased with increase in temperature. Okay, if you observe some examples for paramagnetic substances, there may be vanadium plus 3 or copper plus 2, gadolinium plus 3. All these are example for paramagnetic substances. Here, if you observe the complexes, here hexacyanoferrate, ferrate, here iron is in plus 3. In the case of diamagnetic substances, iron is plus 2. The other one is hexafluorocobaltate. These are some examples for paramagnetic substances. Okay, next one is ferromagnetic substances or ferromagnetism. These substances have large number of unpaired electrons. In the case of paramagnetic substance, they have unpaired electron. They may be one or more than one. But in the case of ferromagnetic substances, the compounds or substances generally have more or large number of unpaired electrons. Generally, if you observe the arrangement of the or alignment of these unpaired electrons, generally they aligned only in a particular direction. It may be clockwise or it may be anti-clockwise. That is, all the unpaired electrons are in one direction only. They are arranged in only one direction. So the magnetism or the induced magnetic field strength will be high when compared to paramagnetism. So it is considered as ferromagnetism. These substances act as permanent magnets. So the compounds or substances which shows ferromagnetism generally acts as permanent magnets because they have lot of unpaired electrons which are arranged only in a particular direction. It may be clockwise or it may be anti-clockwise. So the amount of field strength or the amount of induced field strength will be very high. So they act as permanent magnets. Okay, fine. Next, here the ferromagnetism generally changes with temperature as in the case of paramagnetism. Paramagnetism also changes with temperature, generally inversely proportional to temperature. Here also in the case of ferromagnetism also changes with temperature. Generally it decreases gradually with increase in temperature, and that is, it is inversely proportional to temperature. That is, ferromagnetism decreases gradually with increase in temperature and becomes a paramagnetism or paramagnetic substance at a particular temperature or at certain temperature. That is, generally ferromagnetism depends on temperature. That is, starting with increase the temperature, the ferromagnetism gradually decreases to some point or some temperature. After that, that is, after reaching certain particular or certain temperature, the ferromagnetism converted into paramagnetism. Here, this temperature, that is the temperature at which ferromagnetism converted into paramagnetism or ferromagnetic substance converted into paramagnetic substance, generally known as Curie temperature or Curie point. That is, the temperature at which a ferromagnetic substance converted into paramagnetic substance considered as Curie temperature or Curie point. If you observe example for ferromagnetic substances, they are mainly iron, cobalt, nickel, and gadolinium. Even in atomic state or elemental state, they act as magnet or they show magnetism. Generally, due to the presence of large number of unpaired electrons, they shows ferromagnetism even in elemental state. These are a best example for ferromagnetic substances: iron, cobalt, nickel, gadolinium. Next one is, the fourth one is antiferromagnetic substances. These substances, that is antiferromagnetic substances, also have large number of unpaired electrons which are arranged in opposite or antiparallel directions. Hence, they exhibit antiferromagnetism. Here, anti indicates it is opposite. Antiferromagnetism means it is opposite to ferromagnetism. Even though or although these antiferromagnetic substances have large number of unpaired electrons, their magnetic moment is less when compared to ferromagnetic. Their behavior is generally opposite to the ferromagnetic substances, even though they have large number of unpaired electrons. It is because of, in the case of antiferromagnetic substances, within the crystal lattice, the arrangement of unpaired electrons on one metal atom or one element is quietly opposite to that of the other element which is present adjacent to the first atom or element. That is, the two atoms or metal ions present in the crystal lattice side by side have antiparallel spins of the electrons. That is, the side by side atoms or ions have large number of unpaired electrons with antiparallel orientation. So mutual cancellation, spin cancellation takes place. So they act as antiferromagnetic substances even though they contain large number of unpaired electrons. Okay, fine. Here, in the case of antiferromagnetic substances also, the antiferromagnetism generally changes with temperature. Generally, at starting, it increases with temperature. Because it may be due to the, by increasing the temperature, the arrangement of the antiparallel arrangement of the unpaired electrons may convert into somewhat parallel direction. That's why the magnetism will be increased. It is the reason. Okay, that is, at first the magnetism value increases with temperature, but at certain temperature, after reaching certain temperature value, the substance convert into paramagnetic substance. This temperature, that is where the antiferromagnetic substance converted into paramagnetic substance, considered as Neel temperature. That is, in the case of ferromagnetic substances also, by increasing temperature, the magnetism value radially decreases, but at certain point they converted into paramagnetic substances. That temperature generally known as Curie temperature. That is, the temperature or the point at which ferromagnetic substance converted into paramagnetic, generally known as Curie temperature. So here also, in the case of antiferromagnetic substances, the magnetism of the antiferromagnetic substances gradually increases, starting with increase in temperature. But after some time, when the temperature reaches at certain point, then the substance converted into paramagnetic substance. This temperature, that is, the temperature at which antiferromagnetic substance converted into paramagnetic substance, considered as Neel temperature. Okay, you must remember Curie and Neel temperature. Curie means ferro conversion into para. Neel means antiferro conversion into para. Okay, fine. If you observe the example for antiferromagnetic substances, the best examples are manganic oxide, manganese sulfide, iron oxide. These are the best example for antiferromagnetic substances. Okay, fine. Next, if you observe the electron arrangement or spin arrangement of the electron in different substances. In the case of paramagnetic substances, all the spin orientation are random. In the first picture depicts the arrangement of electron spins in paramagnetic substance. They are arranged in random direction. But in the case of ferromagnetic compounds, that is the second picture, all the unfed electrons are in one direction. All are in one direction. They are clockwise direction. Here, in the case of antiferromagnetic substance, even though it contains large number of unfed electrons, but they are arranged in antiparallel direction. If you observe the side by side elements or ions, if you observe the arrangement of these or the first elemental electron spin, here the adjacent one is opposite. The first one is clockwise, this adjacent one is anti-clockwise, anti-clockwise, clockwise. So here, due to the arrangement of antiparallel arrangement in the antiferromagnetic compounds, they shows opposite behavior to the ferromagnetic compounds, even though they have large number of unfed electrons. In the case of diamagnetic substances, all the electrons are spin paired. That is, there is complete spin paired. Okay, fine. Next. Next, calculation of magnetic moments or calculation of magnetic moments. Generally, the magnetic moment denoted by mu symbol. It is mu symbol. Here, generally, the magnetic moment or gives information. Here, the mu, that is magnetic moment, gives information about the magnetic strength and magnetic orientation of a particular substance. That is, the magnetic strength as well as the magnetic orientation of the substance is generally measured in terms of magnetic moment. That is, magnetic moment gives information about the strength of the magnetic as well as its orientation. Okay, here the magnetic moment, it is a vector quantity or a vector property because it has some value as well as it is arranged in a particular direction. So it is a vector property. Generally, it is measured in Bohr magneton units. It is measured in BM units, Bohr magneton units. Magnetic moment of a paramagnetic substances. In the case of diamagnetic substances, there is no magnetism. It is repelled by the external magnetic field. So there is no need to measure the magnetic moment, or the diamagnetic substance don't have any magnetic moment value. So in the case of paramagnetic substances, they may be ferro or antiferro based on number of unfed electrons. So if you take paramagnetic substances, in the case of paramagnetic substance, the magnetic moment value is generally calculated by using a formula, that is this one. By using this formula, we can calculate the magnetic momentum value of a paramagnetic substance. Here mu is mu s plus L. Mu s plus L is equal to square root or under root 4s into s plus 1 plus L into L plus 1 Bohr magneton. That is, by using this equation, we can calculate the magnetic moment value of any paramagnetic substance. Here S, capital S is total spin of electron. Capital L is total orbital angular momentum of electrons. That is, generally there are four spin quantum number per electrons in an atom. They are principal quantum number n, orbital angular momentum or azimuthal quantum number, that is L. The third one is magnetic quantum number small m. The last one is spin quantum number, that is small s. So here s is total spin of electron, L is total orbital angular momentum of electrons. Here, so according to this equation, mu s plus L equation, the magnetic momentum is not a single component. It is composed of two components. They are, one is spin angular momentum component mu s, and the second one is orbital angular moment component, that is mu L. That is mu equal to mu s plus mu L, which is nothing but mu s plus L. Here, what is mu s and mu L? The first one is spin angular momentum. Mu s is nothing but it is the due to the electron spin, that is magnetic moment obtained due to the electron spin, that is spin of the electron around its own axis. When the electrons spin around on their own axis, the amount of magnetic moment produced generally known as spin magnetic moment. The second component mu L, that is orbital angular momentum. Mu L is nothing but it is the magnetic moment produced due to the electrons rotation around the nucleus. Due to the rotation of electrons around the nucleus, there is some magnetic moment which is nothing but orbital angular momentum. Okay, fine. Next, but in the case of transition metal complexes, in order to calculate the total magnetic moment of transitional metal ions in their complexes, the orbital angular momentum value we have to nullify, or we have to neglect the mu L value in the case of transition metal complexes. Magnetic moment values or magnetic moment calculation, because in the case of these complexes, that is transition metal complexes, the orbital angular moment mu L is generally quenched out due to the direct interaction of the metal d orbitals with the electric field produced by the ligands. Here there is a direct interaction in between the metal d orbitals and electric field of the ligands. Here in the case of transition metals, the d orbitals are generally less shielded by the sp orbitals. So there is direct interaction of d orbitals with the incoming ligands during the complex formation. So due to this direct interaction, there is a mutual cancellation of orbital angular momentum. That's why the orbital angular momentum is generally quenched out in the case of transition metal complexes. But in the case of lanthanides and actinides, that is in the case of complex inner transition metals complexes, we have to take into consideration of the value of orbital angular momentum also, because due to the situation of or location of f orbital far inside in the nucleus, there is no direct interaction in between the electric field of the ligands on the f orbitals. So there is no quenching of orbital angular momentum in the case of inner transition metal complexes or F a block elements complexes. They may be lanthanide or actinide. Okay, fine. So in the case of transition metal complexes, mu L is 0, it is quenched out. So the total magnetic momentum value we can write as mu s. There is no L component, so mu s plus L equal to mu s. So mu s equal to and a root 4 s into s plus 1 Bohr magneton. So this is used to calculate the magnetic moment in the case of transition metal complexes. Here S is total spin of the electrons, as we discussed in the previous slide. Generally total spin is it is always equal to n by 2 value, where n is equal to total number of unpaired electrons, n equal to number of unpaired electrons. So if you take off of the number of unpaired electrons, we get total spin. So by substituting this S value in the equation, that is mu s equal to under root 4s into s plus 1 equation, that is in this equation sorry, if you substitute s equal to n by 2 value, then we get a final value, that is mu s spin orbital angular momentum, mu s equal to under root n into n plus 2. It contains only spin of the, or it contains only spin component of the electrons. So this equation generally known as spin only formula. This spin only formula, that is mu s equal to under root n into n plus 2 value, or equation generally used to calculate the magnetic momentum of transition metal complexes. Okay, fine. Here n equal to number of unpaired electrons. Okay, fine. Next, so observe the relationship in between the number of d electrons or number of unpaired electrons in the in d orbitals and the corresponding magnetic momentum according to experimental data. The first row is configuration, that is d configuration, where it indicates number of unpaired electrons according to equation, that is sorry, the magnetic momentum is mu s plus mu l, it is l into l plus 1 plus 4 into s plus 1 under root or whole power 1 by 2. If number of electrons is 1, it must equal to 3. Only spin only, according to spin only formula, or spin angular momentum value is 1.73 in the case of transition metal complexes. But according to experimental or experimental observation at 300 Kelvin temperature, if the number of electrons equal to 1, then the experimental value, magnetic moment value, must be 1.7 to 1.8. There are 2 electrons, it must be 2.8 to 2.9. 3 electrons, it must be 3.7 to 3.9. 4 electrons, 4.8 to 5. 5 electrons is 5.8 to 6. 6 electrons, it is around 5.1 to 5.7. 7, 4.3 to something. 8 electrons, 2.9, 3.9. 9 electrons, it is 1.7 to 2.2. In the case of 9 electrons in the d orbital, that is, it contains only one unpaired electron. So the one unpaired electron value is generally 1.73. So around it is 1.722. Okay. In the case of 8, 10 electrons in d orbitals, they are completely fade. So there is no magnetic momentum. In the case of 8 electrons, 5 plus 3, 8. So that is 3 orbital completely fade, only 2 have unfade electrons. So the value generally is equal to 2.9 to 3.9 according to this data. Okay, go through this picture or this table in order to find out the relationship in between the number of unpaired electrons and the corresponding experimental mu value. Okay, fine. Next, if you observe the some examples, that is observe the calculation of magnetic momentum values of transition metal complexes according to spin only formula, that is spin angular momentum values of the transition metal complexes. The first example, it is first example complex compound is hexa aqua iron ion. Here iron is in plus 3 state, so iron atomic number 26, electronic configuration, outer electronic configuration 3d6 4s2. But in the case of iron plus 3, Fe plus 3, the outer electronic configuration must be, it is 3d5. losses 2 electron from 4s and 1 electron from 3d, so it is 3d5. So if you observe the electron arrangement in free metal ion as well as in complex compound, in the case of free metal ion, here all the 5 electrons are present in 5 d orbitals, that is each d orbital contains single electron. During the formation of complex with aqua ligands, d orbital splitting takes place according to CFT. It is octahedral complexes, so T2G set comes lower energy level, EG set goes to higher energy level. This is the splitting of d orbital in octahedral complexes. Here the ligands, 6 ligands are aqua ligands. They are generally weak ligands. So the energy separation or the energy gap, that is delta O, is generally less in the case of weak filled ligands. So all the 5 electrons generally, if you observe the arrangement, the first 3 electrons enter into sorry, first 3 electrons entered into 3 T2G orbitals, that is T2G3 electron configuration, and the remaining 4th electron don't enter into T2G. Instead of entering into T2G, it enter into EG, because there is small energy gap separation in between T2G and EG. If the 4th electrons enter into T2G orbital, then it must spend some energy in order to overcome the interactions within the T2G orbital. It is nothing but fairing energy. It must spend some fairing energy. So due to the weak field ligand, the fairing energy here in this case, the fairing energy phi, if we take it as P, the fairing energy always greater than the delta O. So due to this fairing energy higher than the delta O, the electron, that is 4th electron and as well as 5th electron, easily enters into EG set. So the electronic configuration of the complex is T2G3 EG2. So there are number of unfaired electrons are 5. All the 5 orbital contains single electron as in the case of pre-metal ion. So number of unfaired is 5 according to spin-on formula. Mu s equal to under root n into n plus 2. So by substituting n value 5, n equal to 5 value, we get mu s equal to square root 35, which is equal to, according to experimental value, it is nearly equal to 5.92 Bohr magneton. Okay, next example is hexacyanoferrate complex. Here the central metal is iron. Its electronic configuration, atomic number is 26, electronic configuration is 36 4s2. But here iron is in +3 oxidation state, so its outer electronic configuration is 3d5 as in the case of first example. So if you observe the electron arrangement in pre-metal ion and in complex compound, in the pre-metal ions, all the 5 electrons occupy 5 d orbitals. But in the case of complex compound, due to the strong field ligand, that is cyanide, like 6 cyanide strong field ligands, the 5 d orbitals split into 2 sets. That is, it is also an octahedral complex. So T2G set gets lower position, EG set gets higher position, but the energy gap is very high. That is, energy separation delta O is very high when compared to the first complex, that is in the case of aqua complex. Okay, due to this high energy gap, if you observe the filling of electrons, the first 3 electrons enters into 3 T2G orbitals. The 4th electrons has 2 chances. It may be enter into T2G orbital by fairing into T2G orbital, or it may enter into EG set. But if it enter into T2G set, it must spend some fairing energy. If so, in order to neglect or in order to overcome this fairing energy, it may enter into higher energy, the EG set. But in this case, that is in the case of hexacyano complex, that is in the case of strong field complex, here the energy separation is very high. So in this case, here in this case, P is less than delta O. P is less than delta O, that is fairing energy less than delta O. That is the case of strong field ligands, energy gap or energy separation in between the two sets is very high. So fairing if we compare the energy gap with the fairing energy is less than the energy separation. So the electrons easily enter into the T2G set only, that is fairing of electrons take place. So all the 5 electrons generally occupies T2G set only, that is the electronic configuration of the complex is T2G5EG0. So here the 2 T2G orbital contains paired electrons, the 1 T2G orbital contains single electron. So number of unpaired electrons in the complex is only 1, n is equal to 1. So according to spin only formula, it is mu s equal to root 3, or finally it is mu s equal to 1.73 Bohr magneton. That is 1, if there is one unpaired electron, it is according to experiment that it is around 1.73. So 73 Bohr magneton. Okay, in the case of weak field ligand, energy gap is small. So then when compared to fairing energy, the fairing energy is higher than the energy separation. In the case of strong field ligand, energy gap is high, so fairing energy is less than the energy separation. Okay, please remember these 2 points: weak field, strong field, and the relation in between the fairing energy and the energy separation. Okay, fine. Next, third one is tetracarbonyl nickel. Here the central atom is nickel. The atomic number is 28, that is outer electron configuration 3d6 4s, sorry, 3d8 4s2, 28, so 3d8 4s2. Here nickel present in atomic state, there is no ionic state in the complex, so the electronic configuration is 3d10 4s2. If you observe the arrangement, here nickel free nickel metal atom, here nickel complex, here cobalt also strong field, so it is a tetrahedral complex. So if you observe the splitting pattern according to CFT, the EG set gets lower level, T2G set higher level, which is quietly opposite to the octahedral complexes. So the first 4 electrons enter into each set because due to the higher energy separation. After that, the remaining 6 electrons enters into T2G or T2 set. So all the 5 orbitals completely filled, as in the case of pre-nickel metal. So there is no unpaired electron. Unpaired electron is 0. So Bohr magneton is 0. That is mu s value is 0. The fourth example is tetrachlorocobaltate ion. Here the central metal is cobalt, atomic number 27, outer electronic configuration 3d7 4s2, but it is present in CO plus 2, that is cobalt plus 2 state. So outer electronic configuration is 3d7, it loses 2 electrons from 4s. If you observe the electron arrangement in free ion, that is it contains 3d orbitals contains single electrons, and the 2 3d orbital contains paired electrons. In the case of complex, if you observe the arrangement, here chlorine, that is chlorides, are weak field ligands, so the energy gap is small. So the first 2 electrons enter into EG orbitals. After that, the other 3 enter into T2 set. That is totally 2 plus 3 5. There are 7. The remaining 2 enter into EGZ. Okay. If you observe the number of unpaired electrons, there are 3 unpaired electrons in the T set or T2G set. The electronic configuration of the complex is Eg4 T2 3. Number of unpaired electrons is 3. So according to spin only formula, mu is equal to under root n into n plus 2. By applying n equal to 3, we get n equal mu is equal to root 15, which is nothing but mu is equal to 3.87 Bohr magneton. Okay, fine. Next, these are the example for some example for calculation of magnetic momentum in the case of transition metal complexes. Please go through some more examples. Okay, fine. Next, magnetic susceptibility. It is denoted as chi. It is chi. Symbol is chi. Here, if you place any particular substance in the external magnetic field, then there is a induction of some magnetic field, which is nothing but induced magnetic field due to the alignment of the or arrangement of the directions of the induced as well as external magnetic field orientation. They may attract or they may repel. If they are in parallel direction, they are attracted. If they are both are induced as well as external magnetic field lines are in anti-parallel, then they repelled each other. So during this attraction, the magnetic lines of the external magnetic field flow through the substance. Then the substance said to be magnetized. That is, movement of the magnetic lines through the substance when it is placed in the external magnetic field, generally known as magnetization of that particular substance. Here, the amount of magnetization generally given by I value. The amount of magnetization of a particular substance per unit volume in the presence of external magnetic field, that is H0, generally called as volume magnetic susceptibility. That is, it is called as magnetic susceptibility of a particular substance per unit volume. That is, generally in the case of paramagnetic substances, if you place a paramagnetic substances, in the case of diamagnetic substance, there is no flow of magnetic lines through the substance. So it is observed only in the case of paramagnetic substances. If you place paramagnetic substance within the external magnetic field, the magnetic field lines of the external magnetic field generally flow through the paramagnetic substance. Then the paramagnetic substance generally known as magnetized. So the amount of magnetized is generally given by I. If the amount of magnetization of a particular substance per volume within the external magnetic field, generally known as magnetic susceptibility, it is per unit volume. That is magnetic susceptibility per unit volume. It is generally denoted as K. Magnetic susceptibility or magnetization of a particular substance within the external magnetic field per unit volume, generally known as magnetic susceptibility per unit volume or volume magnetic susceptibility, which is denoted as K. Here K is nothing but K is equal to I by H0, that is magnetization divided by strength of the external magnetic field, that is volume magnetic susceptibility. K is nothing but I by H0. Here magnetic susceptibility generally indicates the strength or the amount of magnetization of paramagnetic substance within the external magnetic field. Okay, volume susceptibility is K, which is nothing by I by H0. If D is density of the substance, if you divide the volume susceptibility by D or with D, that is, if you take K by D value, it is known as Gram susceptibility. G means gram, that is gram susceptibility is K by D, where K is volume susceptibility, that is magnetization of a particular substance per unit volume in the external magnetic field. Okay, fine. if we multiply the gram susceptibility, that is Chi value, with molecular weight, then we get molecular susceptibility, which is denoted as Chi m. The volume susceptibility is K, gram susceptibility is Chi g, the molar susceptibility is Chi m. Chi m generally denoted expressed as Chi m is equal to K by D into m, or it is all equal to Chi g into m, because K by D is nothing but Chi g into m. Okay, here the magnetic susceptibility is generally used to calculate the magnetic moment of this substance. What is the use of this susceptibility, magnetic susceptibility? Generally, it is used to find out the magnetic moment value of the substance, because we can't calculate the magnetic moment of a particular substance directly or by experimental data directly. So, by calculating magnetic susceptibility experimentally, we can calculate the magnetic moment using chi value. Okay, fine. Next, here there is a relation in between the magnetic moment as well as molar susceptibility, molar magnetic susceptibility of a particular substance. By using that particular relation, we can calculate the magnetic moment. Here the relation is mu square equal to 3 kT chi m by n mu 0, 3 kt chi m divided by n mu 0, or mu equal to under root or square root 3 kt chi m divided by n mu 0. Here if you observe the one by one what are the terms in the equation. Here mu is magnetic momentum or moment, k is equal to Boltzmann constant. Its value is generally 1.3805 into 10 to the power minus 23 joule per Kelvin. T is equal to absolute temperature, that is temperature in kelvins. Chi m is equal to molar susceptibility, that is the susceptibility of a molecular weight or 1 molar substance. Susceptibility of 1 molar substance is nothing but molar susceptibility. Mu 0 is permeability of air, and its value is 4.7 h per m, h per m. Okay, n equal to, I have got a number, its value is 6.023 into 10 to the power 23, that is number of molecules present in 1 mole. How can we calculate or determine the susceptibility, magnetic susceptibility? That is experimental determination of magnetic susceptibility. Generally, method used for experimental determination of magnetic susceptibility is Gouy method. Gouy method is frequently used to determine the magnetic susceptibility value of any particular substance. Here, it contains a specific balance, which is nothing but Gouy balance. Here, during the use of the balance, we have to calibrate the balance. So, in order to calibrate, we have to use a particular compound, which is nothing but mercury tetrathiocyanate of cobalt 2 complex. The structure is, that is mercury tetrathiocyanate of cobalt 2 complex is used to calibrate the Gouy balance in order to use to determine the susceptibility. In this method, the substance, that is the sample, is generally taken in a small sample glass tube. There is a small glass tube which is known as sample glass tube. We have to take the substance in that particular glass tube in the form of liquid or in the form of powder. Okay, fine. Next, here the cross section of this sample tube is generally, it is A. Now, after filling the compound in the sample glass tube in the form of liquid or in the form of powder, we have to weight the sample tube along the sample in the absence of external magnetic field. After filling the compound, we have to weight the sample tube in the absence of external magnetic field. Now, place this sample tube, which is hanged from the one side of the balance, so of the Gouy balance in strong magnetic field with the value is magnetic field strength is H, and measure the weight along the sample, that is without placing the sample tube in the external magnetic field. First we have to calculate the weight of the substance. After arranging or attaching the sample tube to the one side of the one side of the Gouy balance, we have to place the sample tube within the external magnetic field. Then we have to weight, or we have to measure the weight of this sample tube in the presence of external magnetic field. Then we get some difference in the weights of the sample compound if it is a magnetic compound. Okay, then the weight difference, if we consider the weight difference, that is the weight of the substance, magnetic substance in the absence as well as in the presence of external magnetic field as delta M, and the earth gravitational force as G, then the force which is acting on the substance in the presence of external magnetic field F is equal to generally delta Mg. If K1 is volume susceptibility of substance and K2 is volume susceptibility of air, air volume susceptibility K2 value is generally 0.364 into 10 to the power of minus 12. Then the force acting on the substance in the presence of external magnetic field during the measuring of the weight F is equal to K1 minus K2 into A into mu 0 H square into H square divided by 2, that is F equal to of K1 minus K2 into A mu 0 H square. Okay, here therefore from this equation we can modify this equation. K1 equal to K2 plus 2 delta Mg by A mu 0 H square. By substituting all these values, that is K2, delta M, as well as G value, A cross section area, mu 0 as well as H square values in this equation, that is K1 equal K2 plus 2 delta Mg by A mu 0 H square equation, then we get K1 value. We know susceptibility equation, that is molar susceptibility equation, which is nothing but chi m equal to K by D into M. Chi m equal to K by D into M. That is molar susceptibility value equal to gram susceptibility into molecular weight. Here gram susceptibility value can be obtained by this equation, that is K1. By substituting this K1 value here, we get chi m equal to M by D into 2 delta Mg by A mu 0 H square. We get chi m value, that is molar susceptibility value from the K1 value. Okay, we know the relation in between the molar susceptibility and magnetic moment, that is mu equal to under root Kt chi m by N mu 0. So from this equation we can calculate magnetic moment of the substance by substituting chi m value from here, which is obtained from here, as well as Avogadro number, mu 0 values, K Boltzmann constant, absolute temperature values, we get the final value, that is magnetic moment of the particular compound. This is the method, that is Gouy method, which is used to find out the magnetic susceptibility. From that we can calculate the magnetic moment of that particular compound. Okay, fine. Next, here the picture depicts the Gouy balance, which is used in Gouy method to determine the magnetic susceptibility after that magnetic moment. Here it is the balance, it contains two plates, just like a balance, normal balance. Here by remove one of the plate from the balance, we have to hang the sample tube which is filled with sample. The blue color is sample. It is sample tube which is hanged from the one side of the balance by removing the plate. We have to place this sample tube along with the sample within the external magnetic field. Here these two are north and south poles of the external magnetic field, that is electromagnet. Then if you place this sample tube within the external magnetic field, then if the compound is magnetic substance, then it is attracted by the compound, then the balance comes down, then we get more weight. We get more weight than the weight of the sample when it is in the absence of magnetic or in the absence of external magnetic field. So there is some mass difference in the sample in the presence as well as in the absence of external magnetic field. From that value we can calculate the susceptibility as shown in the previous slide by using various formulas. Okay, fine. This is all about the magnetic properties of transition metal complexes, types of magnetism, as well as calculation of magnetic moment values of some transition metal complexes by using spin only formula, as well as determination or calculation of magnetic moment or magnetic susceptibility by using Gouy method. From that value we can get or we can calculate magnetic moment. Okay, fine. Next, thank you very much for your patience and for watching this video. Thank you one and all. Okay, bye.